non-making of dis. Shoot, I heard a question.
For some reason, I just have a lot of trouble identifying angular and disconformities. Can you explain it one more time what the difference is? I mean, non and disconformities. I understand angular.
Yeah, the angular should be, that's the key. Angular is usually the easiest to identify because it's only between said rock layers, but the said rocks are oriented in different ways. For the let me just run it. We have to have tremendous amount of erosion to expose rocks like granite or schists, any kind of igneous or metamorphic rock that would have formed deep underground. In order for sediments to have been deposited on top of it, there had to have been tremendous amount of erosion to expose those deeply seated rocks at the surface. And then I'm going to have said rocks deposited directly on top of non-said rocks. That's what the non means. The non-conformity is said rocks deposited on non-said rocks. So igneous or metamorphic. Because an angular and then the disconformity, those are all dealing only with said rocks. Angular, said rocks orient different orientations, tilted different ways. A disconformity is the hardest one to recognize because the said rock layers are not tilted relative to each other. It's just showing you that there is a missing time, that the rock unit, the sequence is not continuous. It doesn't match or doesn't equate to a consistent record. It's not a continuous record. And so this model of a disconformity is showing erosion causing that gap. So some rock layers were removed by erosion. There's our gap in time. And so the key is that disconformity is only between said and said. That's why I remembered this as an S in it. For non, doesn't. And Evan's asking about fossils, and the answer is sorta. Fossils are oftentimes the easiest way. But there can also be things like the principle of inclusion. I might have chunks. In fact, the non-example here shows us that. I might have chunks, inclusions of the underlying rock. So I know this is showing you for a non-conformity. Oops. Let me zoom ahead here. But I could have chunks like this in the disconformity too. These would be chunks of the rock unit that was below in the disconformity. The other is sometimes the contacts are usually very abrupt. The contacts between the layers above and below a disconformity. Let's go to the disconformity. The rock units above and below the disconformity are often dramatically different from each other. So oftentimes fossils is the most definitive way, but I might see inclusions, this light gray rock here, that I might find chunks of that light gray rock in the brown. And so the principle of inclusion would say, well, those light gray chunks must be older than the brown layer, telling us there had been erosion to produce those chunks of light gray if I'm finding them in the brown. But also I could have a very abrupt contact. Say this is limestone and this is conglomerate. Limestone and conglomerate are vastly different kinds of rock, vastly different kinds of environments. But fossils are usually the most definitive. So Evan, does that help? Okay, Melissa, did that help? I think you were the one that asked this question. Okay. Again, that's how I learned it. Disconformity has said rocks in it. Angular is pretty self-evident. But making sure you're using the right term, whether it be disconformity or non-conformity. Remember, a non-conformity has non-said rocks involved. So igneous or metamorphic. Then we talked about this idea of uniformitarianism, the present is the key to the past. We'll be talking about that a little bit later as well. Evan, you are correct, but you can backtrack. The questions will be randomized, and show up one at a time. But what it is, I believe, when you first enter the exam, there'll be a banner above the question with a bunch of numbers. I think there's like 33 questions on this. And you can click on any of those numbers and it'll take you directly to the question. So my suggestion is have a piece of, there are no videos. No, just pictures. The lab test that we had is the only one of videos. I don't believe there's videos in any other exam. But the banner across the top of the numbers, you can click on those numbers and it will take you directly back to that question. So my suggestion is have some scratch paper with you. And if you have a question like, damn, I don't know what that answer is, write down the number of the question, skip it, and go back to it. See what I'm saying? So you don't have to scroll through every question. You can actually click right to that question. But you have to write down the number of the question so you don't forget. Cross-cutting relationships, principled inclusion. These are important ideas that allow us to determine, sort of the sequence of events of relative dating. Will Smith with his fossil correlation. And remember, the geologic time scale is a scale of time. And again, I'm not going to, I think I've mentioned before, it'd not be fair to me to make you do all of this, but I do expect you to know the biggies. I expect you to know some of the eras and eons. But we're not going to worry about periods yet. Because they're not that many. There's 4 eons and 3 periods. So not that many. You remember the prefixes. Paleo is old, Ceno is new, Meso is middle. So Ceno is not going to be newer than Meso, which is going to be newer than Paleo. So I'm not going to worry about this. But this is the one thing that was confusing. It was confusing to me. Time rock units. And remember, the time scale was figured out by time rock units. This sequence of rock has fossils that are distinct and different from this other sequence. So I'm going to call this the Cambrian system of rock, establishing a time rock unit that we'll call the Cambrian system. And this rock layer up here is going to be the Ordovician system of rock with its own fossils. And then the Cambrian system of rock was deposited during the Cambrian period of time. The Ordovician system of rock deposited during the Ordovician period of time. So remember, rock units are not time units. Remember, there's 3 things we talked about. There's time units, rock units, and time rock units. Time units, as the name suggests, are units of time. Rock units are obviously units of rock. And time rock units are still units of rock that were deposited during the same interval of time. It'd be fair for me to mention that, is a period longer than an era? That would be a reasonable kind of question, but I'm not going to make you worried about all the details of this. Because we'll put it later this semester. We're going to focus much more on periods and eras and things, and even epochs. So this is more just an introduction to it. Radiometric dating. We talked about the concept of it using radioactive decay. Parents changing into daughter. As time goes by, there will be less and less parent and more daughter. Talk about alpha particles and beta particles, but honestly, this is mainly for interest. And so as time goes by, there'll be more and more daughter being created, more blue daughters and less parent. And so the amount of time it takes for 1/2, go back here a second. So the amount of time it took for 1/2 of the original amount of parent was equal to 1/2 life. And in this case, this radioactive parent, it took 4 months to go from 64 parents down to 32, 1/2. So apparently it's 1/2 life is 4 months. So in another 4 months, it's not going to be 0. In another 4 months, 32 should become what? Let me make this bigger so it's easier to see. What's going on here? Oh, okay. All right, so it took 4 months for 64 parents to become 32 and thus creating 32 daughters. If 4 months is the half-life, that means in 8 months, how many parents should remain? And I can't see, so turn your mics on. Not 0. Took 4 months to go from 64 to 32.
48.
48?
Is that true?
Well, again, I'm talking about parents. Parents are always going to be decreasing, not daughters. But I think you're on the right track.
16?
Let's see. There you go. You don't have to calculate half-lives. I mean, half-lives are standard. You know, there's your half-lives. But am I going to make you memorize these? Hell no, I don't know them. But I expect you to know the concept of radioactive decay and the concept of what a half-life represents. Yeah, maybe. But when you say math, are you talking like division? I would expect people to be able to do division. But again, the goal of this is I'm not going to, since we never really did any exercises like this in any significance, no, I'm not going to make it calculate anything. But the logic of it is what this is more important. How this works, this idea of what a half-life represents, that's all fair game. You know, people get bent out of shape with the math, but again, it's just the idea of, if I start with 64, after one half-life, I should have, what was that, 32. After another, I should have 16. After another, I should have 8. After another, I should have 4. After another, I should have 2. So it's constantly being divided in half. And then we talked about the birthday. And, you know, how does, in what scenarios, in what situations does radiometric dating work? And in what situations is it not? And what is it really dating? You know, remember, it's actually dating when crystals form. That's what radiometric dating is actually doing. It's taking a crystal, looking at what's parent and daughter in that crystal, and from that amount of parent and the amount of daughter, figuring out how long ago that crystal crystallized. That's what it's doing. And so we talked about how it works well with igneous, but not so much with the others. Although not so much for sets, it can with meds. You know, we gave it a scenario of zircons, of how zircons are nice because when they form, they don't have any daughter. They're only going to crystallize with lots of parent, uranium parent. And so as time goes by, the zircon's going to accumulate more and more lead as that uranium that was trapped in it at birth converts to lead. So, yeah, we didn't talk about these dudes. That's it. So geochronology, and again, like I said before, most of this should have been reviewed. Only a tidbit of it shouldn't have been new. Said rocks, again, a lot of review as well. But we got into it probably in a little bit more detail. But this idea of depositional environments and different kinds of said rocks, all that should have been basically reviewed. And then, what was the other one? Minerals, again, most of this is going to be reviewed. In fact, if anything, this mineral discussion is much shorter than what I give in physical, because we're focusing on minerals that either A, are critical for the creation of sediment, or B, important in said rocks. You know, like halite and gypsum, or hematite. Questions? When you say go over minerals a little more, well, remember what a mineral is. I know when you took physical, I'm guessing you went over the 5 criteria. You know, naturally occurring crystalline solid with a definite chemical composition and is inorganic. But of those 5, there's only really 2 that are really important. Having a definite chemical composition and has to have a crystalline structure. And honestly, if it's crystalline, it's automatically solid. So. Those are the two biggies. And remember, minerals made out of chemical elements that are bonding together. And the silicate minerals are based on the silica tetrahedron. 1 silicon and 4 oxygens in this pyramidal shaped thing you do. Well, you're right, but let's go over it. What minerals dominate said rocks? We already went over this once, right? When I say sandstone, what mineral? There you go, quartz. Yeah, could there be feldspar? Yes. But quartz is still going to be the dominant mineral. When I say shale, what mineral? Clay. If I say rock salt or rock gypsum, rock salt, what mineral? If I say rock gypsum, what mineral? If I say chert, what mineral? Think about it. Yeah, junior quartz. Remember, it's microcrystalline. What else are the said rocks are there? Carbonates. Chert is microcrystalline calcium or microcrystalline quartz. It's a chemical. You know, we didn't spend a ton of time on igneous rocks, but I expect you to know what the major igneous rocks are. If I say granite, I expect you to know what that is, or basalt, or peridotite. You know, I expect you to sort of know the biggies. You know, we're not going to get into vesicular and porphyritic and all that. Who cares? That's much more physical. And if I talk about metamorphics, again, I would expect you to know what are some of the primary metamorphic rocks, your schist, your gneisses, your slates, you know, quartzite, marble. Again, we talked about them. We didn't spend a ton of time on them, but you know, put it this way: if I ask you any questions about these things, it's not going to be 4 or 5 questions. It might be 1. We didn't spend hardly any time on it. And we talk about weathering. Remember the creation of sediment. And again, I do expect you to know some of the basics. You know, a lot of what we talked about was like the chemical weathering of granite. Remember, granite is 3 minerals. What are 3 minerals in granite? 3 basic minerals in granite. Yeah, ferromagnesium, feldspar, what else? One more. Certainly magnetic. And quartz. Those are the big 3. And so to sort of recognize as granite chemically weathers, what happens to the ferromagnetes? You know, what's likely to be created by their chemical or physical weathering? What's going to happen to the quartz? What's going to happen to the feldspars? You know, those are, you know, I would expect you to know those, because those are critical when it comes to said rocks. You know, where does how do we get the sediments that we find in said rocks? How do we get the quartz? How do we get the feldspar? The quartz or the clay minerals or the gypsum or the halite? You know, that's the logic of what we talked about in this case, is how chemical weathering is the source of the material that we now find in said rocks. Questions? Sure. When we say no to different evaporates, yeah, it would not be unreasonable for me to ask you, you read 2, rock salt and rock gypsum. But to know how they form, yeah, that'd be fair game. You know, the water evaporates, you're going to get precipitation. You're going to get the formation of crystals from those dissolved ions. So these crystals of halite and the crystals of gypsum will precipitate out of the evaporating water. Questions? All right, Delta is definitely one of the transitional or marine margin environments. And note, I like marine margin, but so very likely on the exam, if I ask for that, I'm likely to use marine margin. I probably won't use transition. But marine margin and transitional are the same thing. So let's go look at that. So delta's one. Give me another one. Anybody have another transitional deposit or marine margin environment? Tidal flat, that's a good one. Beach. Yeah, those are the big three. There's a few others. Lagoon, Barrier Island. But those are the big three. Or big, beach, lagoon, tidal flat, delta. Yeah, I think there's three. And remember, when they're essay, I'm talking short essay, you should be able to give me a reasonable answer in about 3 sentences. If you craft your sentences well, 3 sentences should be plenty. 1 sentence usually is never going to be enough. Not necessarily. I don't remember exactly what they are, honestly. But there might be, you might have to interpret a picture. They might be describing what you'd find or something like that. So, but again, it's going to cover, those essay questions are going to cover, maybe something on geologic time or, said rocks or something. But yeah, I forget exactly what they were. And even if I did, I wouldn't tell you anyway. But Evan, it's not going to be a lot of that about proving a question. Because again, that was dealing with specific depositional environments. You're not going to have to do that on this. Again, the concept of depositional environments is going to be much more factual here. Being able to recognize, like, delta, what is it? Is it low energy or high energy? That kind of stuff. But not interpretive. Or not specifically interpretive like the lab test, where you're just going to look at a rock and have to come up with a depositional environment. Correct, Brandon. Textural maturity and even compositional maturity are only applicable to clastics. And of the clastics, really just sandstone. We talk about who it's in the lab, and the logic is for textural maturity of clastic sediment, it's because clastic sediment started out angular and jaggedy and became rounded or became well sorted during transport. Fluids form round. They never started off jaggedy and became round. So we can't really, there's no interpretation of textural maturity because they never were jaggedy. We'd say nothing from the lab test. The concepts of the lab test, definitely. But you're not going to have the same, you're not going to get a picture and have to interpret, give me a specific depositional environment or anything like that, like the lab test was. But talking about energy, high energy, low energy, the kind of sediment one might find, that kind of logic, yeah, because we talked all about that in lecture. But no, you're not going to get pictures of rocks and have to tell me its depositional environment in the same way. There might be some of this, but nothing like it was on the lab test. I'm still here. When you say rock ID, no, I'm not going to give you a picture. But I might give you characteristics of a rock, Meaning I might give something about its maturity, composition, or texture, and tell me something about it. I've got to interpret it in that way. But no, you're not going to get a picture of a rock or anything like that. Tell me what it is, or a picture of a mineral, and tell me what it is. Again, there is a lot of crossover. But remember what lab is. Lab is learning skills of how to identify rocks, interpret rocks, and things like that. The exam is much more conceptual. So you can understand the foundations of those things. What maturity is, what it really, how do we recognize it, or what kind of sediment might be found in what environments, and what are the generalities of that? Am I likely to find limestone in the desert? That kind of stuff. That is much more lecture-y kind of concept than lab out. But the idea of knowing that, how cross-bedding can be interpreted, or how carbonates can be interpreted, or how, conglomerate can be interpreted. Yeah. Because we did talk about those kinds of things in lecture. No, that is not. Well, maybe. Yeah, I guess she does. But she's not the one that typically visits. But yeah, you can hear her sometimes. You hear the cat screaming a little while ago? Is that what you asked? Yeah, that's her. She doesn't like said rocks. If we were talking about igneous rocks, she'd be silent. Questions. Rock's birthday. Yeah, the logic is this. When we're radiometrically dating something, remember, something forms. The crystal forms, and in that crystal is going to have some radioactive isotopes. And over time, those radioactive atoms in that crystal are going to change into the daughter. So over time, the amount of original radioactive isotope is going to drop, the amount of daughter is going to increase, because what we're really measuring is when that radioactive parent was trapped in the crystal. And so when we talk about the birthday of a rock, when we try to radiometrically date a rock, what we're really talking about are when did the crystals form? The crystals that trap and contain those radioactive parents. And so with igneous rocks, it's fairly easy, because that's exactly how an igneous rock forms, from crystals crystallizing from a magma. And so when we radiometrically date those crystals in an igneous rock, we're dating when they crystallize. But in a metamorphic rock, it's sort of the same thing. New minerals are formed during metamorphism. And so if I radiometrically date those new minerals that were created during metamorphism, then I'm determining when that metamorphism occurred, how many years ago, how long ago that metamorphism occurred. We have to be a little more careful though, because we have minerals that can survive metamorphism, meaning that they were not completely recrystallized. And remember, what we're really wanting to find out is when that metamorphic rock formed, which we're really asking is when did the metamorphism occur? And so we need to find crystals that were formed during metamorphism. And that can happen. So we can radiometrically date metamorphic rocks, but it's not straightforward because we have to be selective on what crystals we're going to be measuring, how much parent and how much daughter. And that's what the problem is with said rocks. Is remember, in said rocks, we want to find out when the sediment lithified, when the sediment became rock. And since, particularly for clastic sedimentary rocks like sandstones and conglomerates and shales and whatnot, they're made from pieces, solid pieces that had their own original birthday. And so when we look at like a sandstone, there's a sandstone that may have lithified 50 million years ago, but it's made out of sand grains of quartz, or maybe some pieces of feldspar that might be much older than that. And if we're radiometrically dating a sandstone, we'll be finding crystals in the sandstone, the sand grains, figuring out how much parent and daughter is in there. We can measure the age of the grain, but we're measuring when that grain crystallized, not when the said rock was lithified. Then it's like taking your house. If you have a house that is made out of local rock, like our local limestone, a lot of our homes around here are made with the white blocks of limestone. Well, that limestone is 100 million years old. That don't make your house 100 million years old. And so that's the problem with trying to radiometrically date said rocks, because radiometric dating is determining how long ago a crystal formed. And because said rocks form from, at least plastic said rocks, form from sediment that already existed before lithification, it's difficult, if not impossible, to radiometrically date when sediment lithified unless I can find specific crystals that only formed during lithification. And those actually are not that common, and the ones we do have usually don't have a lot of radioactive parent in them. That's the problem. So igneous rocks, not a problem. Metamorphic rocks, for the most part, not a problem. Sedimentary rocks, a bit of a problem. So radiometric dating doesn't work well, because if we radiometrically date a crystal, we're likely to find the crystal is much older than the date of lithification, which is what we really want to know. It is, but you have to be very careful, because what you're really looking for are minerals or crystals that would have formed during lithification. And for the most part, it doesn't work very well. So it's possible, but you got to be really careful. And most of the time, it's simply not done. Usually there's other ways, like we already talked about this way, like where you're using relationships between said rocks and igneous rocks, which are more accurately radiometrically datable. That's how we really can figure out the ages of said rocks. We're not radiometrically dating the said rock itself. So it can be more tricky. And what and right now, I have to admit too, most of the time we determine ages of said rocks by fossils. We've done enough radiometric dating of igneous rocks in relationship to said rocks that we have a really good feel now of what the ages of certain fossils are. We're not radiometrically dating the fossils, but once we radiometrically date a said rock that contains those fossils, if I find those fossils somewhere else, I know the age of that rock, because I already know the age. I've already figured that out by not radiometrically dating the fossils, but by radiometrically dating rocks that are radiometrically datable in relationship to the said rocks. Does that make sense? So, yeah, that's the logic of it. That help, Abigail? Good question. Questions. So let me ask you guys a question. Did we spend more time on said rocks and depositional environments and in geologic time than we did on talking about igneous rocks? We're talking about minerals specifically. We're talking about metamorphic rock. So what I'm saying is you should expect there to be far more questions about things we spend a lot of time on. Not to say there won't be any questions about minerals or igneous rocks or maybe metamorphic rocks, but you know, you should. One thing that you can commonly do is when you're going through your notes or taking notes for the class, might jot down things that I'm spending a lot of time on. There's no guarantee that that'll equate to more questions on the exams, but that is a logical assumption. And certain things that I don't spend a ton of time on, I may not ask a lot of questions or any questions about. When you say minerals, again, we didn't spend a ton of time talking about very specific minerals, only those more or less in context with either weathering or in said rocks. You know, we talked about how a granite weathers and what happens to the feldspar in the granite, what happens to the ferromags in the granite, what happens to the quartz. So again, I guess what I'm trying to say is I'm not going to ask you, you know, what is the chemical formula of olivine or, you know, Bowen's reaction series? You know, yeah, some of those concepts were discussed, but the logic is the generalities of it. What minerals are chemically stable? What minerals are not chemically stable? Well, if you're asking about rock ID questions, meaning am I going to give you a picture of a rock and you have to tell me what it is? The answer is no. That's lab. But, you know, I would expect you to know the characteristics of a said rock, like a sandstone comes to, you know, rough grain size or maturity concepts, you know, or how sediment gets altered during transport. Yeah, I expect you to know that kind of stuff. But no, I'm not going to give you a picture where you have to tell me, you know, yes, that's rock salt, you know. That's lab.
So besides the essay questions, then the rest of the test is all multiple choice?
No, most of it is, but there's going to be matching. There may be some reordering. I might give you some scenarios or things. You have to order them in some way. What else? I don't think there's any multiple answers, which is I give you a list of things and you have, you know, choose all that are correct. I don't think there's any of those. I could be wrong. And also too, there might be, I might give you a picture and you have to click on things like, in this picture, where's a beach? You know, that kind of stuff. But yeah, the bulk of it's going to be multiple choice and matching with a few other things.
Cool, thank you.
Correct. Stability, I'm talking, when I say chemical stability, that has nothing to do with its hardness or cleavage. It has to do with whether or not it's chemically stable under the conditions on the surface of the earth. So the logic is minerals with high crystallization temperatures, your ferromagnesians, your calcium feldspars, they don't like it. They do not like it up here. And therefore, they generally do not survive the transport and deposition needed to make a said rock, to make a clastic said rock. It's more stable minerals, your clay, your quartz, and to a lesser extent your potassium feldspars. You know, they do survive transport. They can be transported as solid pieces and be deposited as solid pieces and survive lithification. Ferromags and high temperature feldspars, not so much. Questions? Okay, I'm trying to match this quartz as best I can to as if this was face to face. So I have to admit this Q&A lasts a lot longer than if it was face to face. But it's easier to, do things I can draw on the board or whatnot. I normally teach around Rock in Northridge. My office is technically around Rock. But I haven't seen my office now in months. There might be fungus all over it, I have no idea. Questions? If not, then I can. Brandon asked a question. Okay, Brandon. Oh, I'm sorry, I missed that one. Sorry about that. No, it is not biochemical. I know the Harwood site, not the Harwood site, yeah, the Harwood site, for some reason lumped in coal with the biologics, I think he called it. But that's a terrible, I mean, I hate to say this, but the sedimentary rock people, the sedimentologists, none of them, they can't come to an agreement on how to classify said rocks. But the way I'm going to expect you to deal with said rocks is this way. You're right, that's why igneous rocks are so much better. There you go, plastics, chemicals, biochemicals, and organics. And organic is easy. There's only one, coal. And the logic here is these names for these terms, I think, are much more reflective on how they form. Chemical, we have crystals precipitating from water. That could either be by the water evaporating, leading to precipitation, or organisms extracting ions from the water and making their shells. That's, so that's biochemical. But note, the term precipitate is in both of these. Precipitate by water by evaporation, or at least non-biological ways, or precipitating of ions by biological ways. So, again, the classics, that's your conglomerates, your sandstones, your siltstones, and your shales. Chemicals, I actually have them listed here for the most part. Biochemicals, your carbonates, and organics, your coal. All right, well, if no one has any other questions, I can make the exam available probably about, let's say 2:35. I always like to have about 5 minutes to make sure I didn't catch any last minute boo-boos that I may have made. And remember, you need Locked On Browser for this. Remember, the lab test you don't, but the exams you do. So be sure you have that operating properly on your machine, or you won't be able to access the test. Also remember that best thing to do is give yourself plenty of time. When I say plenty of time, meaning don't wait till 11 o'clock on Wednesday night. I'm sorry, not Wednesday night, Tuesday night, tomorrow night. You have 70 minutes. My suggestion when you take these tests is go through and answer the questions that you can answer easy. And write down the numbers of the ones that you are not as happy with. And so you can go back to those. This is a little different than the advice I gave you on the rock and mineral identification, where I wanted you to give an answer regardless. So it's always good, because by doing it that way, you're guaranteed not to have to backtrack. But there's so many questions on the exam, I think there's like 33. It's probably best to write down the numbers of the questions that you are uncomfortable with, so you can go back to them. And you want to write down the numbers, so you don't have to, so you can just go to that banner where it has all the numbers of all the questions and just click on those numbers to get back. Some questions are meant to be very straightforward. Some questions are not. So the key too is try to read what the question is asking. And remember, the best thing for multiple choice is don't figure out what the right answer is, eliminate the wrong answers. Oh no, Evan, well, no. Are you asking sort of like on the lab test, where you had, here's the picture, is this continental, no, they're all standalone. However, I have to admit, I think there's at least one question that sort of shows up twice, meaning it's the same picture, but it's asking a different question, and you don't need to answer the one question, answer the second question. I think that's the only one. I know I say this, and sometimes, no, yeah, I try not to do that. There's only one that I know of that is sort of, honestly, it's not really sequential at all, but it uses the same picture, but it's asking two different things. What am I trying to say? Yeah, again, I think go through the questions that you think are pretty straightforward, answer those. The ones you are not, write down the numbers of that question, and so you can go back and spend more time on it. The kiss of death is spending too much time on any individual question. And remember, in multiple guess, usually your first choice, the first choice you make is correct. Only go back and change your answer in a multiple choice answer is if you know the original choice you made is wrong. Usually your first guess is the best. There's also, I think, a few bonus questions. I forget how many. Maybe I think there's 2, maybe 3. Don't spend a ton of time on the bonus questions. If you run out of time, skip them. They're not going to hurt you. Only do them if you have time. So if you feel like you're running out of time, skip them. And come back to them at the very end. If you know the answer, obviously answer it. But if you're going to spend time on a bonus question, be sure that you don't spend too much time. I'm trying to think, is there any other advice? Oh, the essay questions, I do strongly suggest maybe even having some scratch paper and handwriting out something a little bit, write down some ideas. Because by doing it that way, the worry is sometimes people spend so much time on the essay questions that they run out of time because they're trying to formulate their answer right then and there. But if you read the essay question, write down some ideas, write down the number, and then come back to it towards the end, might be a better way of doing it. Unless you know you can easily write the answer quickly, then fine, do it. But if you think you're going to be spending some time on the essay question, more time than you'd like, my suggestion is jot down some ideas, write down the number of the question. I guess so. Is that what it works out to be? There's 33 questions, and you have 70 minutes. So, more or less. 2 minutes doesn't sound like a lot, but it is. If you think about a multiple choice question, spending 2 minutes on a single multiple choice question, that's too much time. 2 minutes is slightly shorter than a typical pop song. And not that you care, but if this was a face-to-face class, you would likely get a test with about 50 questions and have 120 minutes to do it, but there'd likely also be more, like probably about 6 or 7 essays. So I don't know what's worse. Again, I'm not trying to say all the questions are easy. Some are going to be very straightforward. Some are going to be a little more challenging. But the key is when the challenging ones come up, don't overthink a lot of this. Read the answers, the choices, eliminate the ones you think are clearly wrong. And usually there's always 1 or 2 that usually are clearly wrong because the answer sounds ridiculous or the answer sounds like something we've never talked about. So, super duper. All right, I guess I talked too long. Let's do it this way. The exam will definitely be up by 2:45. And we get 10 minutes. Make sure there's no last minute tweaks I need to make. Fair enough? Oh, one last little tidbit too. Remember, you're on lab on Wednesday. We're going to be finishing up the geochronology lab, but you're also going to be getting a new lab on absolute geochronology. So the more of the geochronology lab you can get done before you go to lab on Wednesday, the better. You will have some time to work on it, but FYI. Hopefully do, guys. Good luck.